Hi, this year I will go to various Linux events, and wherever it's accepted I want to hold a Linux driver workshop. This weekend I will give the first driver workshop in Chemnitz, and I have to practice it. So I thought, hey, when I'm practicing it anyway, I could also do a video about this so all my viewers on the world can see this or enjoy this workshop. So here I am with my Linux driver workshop, and I want to give you an introduction to Linux driver development. So here is my agenda. First, I will give you a little bit of theory. What is the Linux kernel and what it does? Then we will take a look at how we have to set up a Raspberry Pi in order to use it for Linux kernel module programming. Then we will write a first Hello World kernel module, and in order to compile it, we need a Makefile, which we will create in the next step. Then, in order to insert our kernel module, we need some bash utils to do so. Drivers are mostly about accessing hardware, so we will control some GPIOs in this session today. And last but not least, we want an interface to access our driver from userspace, and therefore we will use device numbers and character-oriented devices. And this will be the next point here. And I also have some backup slides in case we have some time left, so we can talk about GPIO interrupts, I/O control, or how to create device files with udev, or we can also take a look at the device tree if you're interested in one of these topics and if there is some time left. Okay, so now let me introduce you to the hardware we are going to use. So we will do the kernel module development on our old Raspberry Pi 1. And here you can see the hardware for which we will write the driver. So here I have a 7-segment display and an IC translating 4 I/O pins to control signals of the 7-segment display. And the goal for today is to write a driver which can control the 7-segment display. Okay, so let's talk about the Linux kernel. Of course, this is a topic which could take 1 hour talk alone, so I will really break it down for this workshop. So basically, the Linux kernel enables our GNU Linux operating system to run on a variety of hardware. So most of you will have laptops with x86 processors from AMD or Intel, but Linux also runs on our smartphones or on a variety of other processors. And the Linux kernel is responsible for this, because the kernel gives us a hardware abstraction. So what does this mean? This you can see on the right hand side. Let's imagine we have a PC with an old hard disk in it and with a USB stick plugged into it. From a user perspective, when we're saving a file on the USB stick or the hard drive, we don't see any difference in the process in how to save it. So we are just clicking on save and we are selecting a folder or a file in our root file system. But the Linux kernel has to take care of that the data will be transferred over USB if we want to store them on a USB stick, or over SATA if we want to store it on a hard disk. And we as a user, we don't see on which media it will be stored. The kernel is hiding or abstracting this from us. And this is a very cool thing. And another thing the Linux kernel does, you can see on the left hand side. So here you can see I have a system with a single core processor, but there are multiple applications running on this processor. And the reason why this is possible is because the kernel also has a scheduler which will give every application a slice of processor time, or a slice of time at which it will be executed on the processor. Because the time slicing are just a few milliseconds, we as a user, we don't see there are sliced, so for us everything is running in parallel. And of course the kernel don't only has to reserve time slots for each application, it also has to reserve resources like memory, for example, for each application we want to run. And this is also done by the kernel. So in total, Linux is using a monolithic kernel, which means so the kernel is one big binary blob containing all the functionality. So this will contain the scheduler, the drivers, and everything else. But of course, so here on my laptop I have an integrated Intel graphics card. But if the kernel would be a big monolith, then it would mean the kernel must be really big and it must have the Intel drivers, the AMD drivers, and the NVIDIA drivers baked into it, so it can use all display resources. On a design like this, you will get a huge kernel. So the idea, Linux made the following. It gave you the option to use kernel modules, which contains a driver and can be loaded into the kernel dynamically. And this time we get a small Linux kernel with just the most important features into it, and all the other drivers are loaded over kernel modules. So there is a hardware detection state, and then it sees, okay, I'm using an Intel GPU, so I only have to load the Intel drivers into the kernel, and the AMD drivers and the NVIDIA drivers I don't need to load. So this makes the kernel a lot smaller. And in this workshop here, we will only program kernel modules. So how to compile a driver directly into the Linux kernel is another topic. But if you're interested in that, I also have videos on YouTube explaining how this works. Okay, now let's talk how we have to set up our Raspberry Pi in order to use it for Linux kernel module programming. So first we need to install the kernel headers. The kernel headers are all the necessary header files and makefiles which are needed in order to compile a Linux kernel module for your currently running kernel. On Raspberry Pi OS, you can install them with sudo apt install Raspberry Pi kernel headers. But of course, before you do so, make sure to update your package sources and also upgrade your system. Why is this required? Well, Raspberry Pi kernel headers will install you the latest kernel headers, or the kernel headers for the latest kernel. And if you're running an older version of the kernel, you will have a mismatch. And it's important that the kernel module is compiled against the kernel headers of your currently running kernel. If there is a mismatch, you won't be able to load it. So make sure to run a system upgrade, which will also update your kernel if it's an older version. So in order to build our kernel modules, we will need the GNU-C compiler and we need Make for running Makefiles. These two applications are bundled in the Build Essential package in Debian, so I would highly recommend you to install it. And then, in case this upgrade has installed a new kernel, we need to reboot our Raspberry Pi so the new kernel is loaded and the Linux kernel headers are matching to our or running kernel. So this is quite important. Okay, so now let's take a look at the first Hello World kernel module. So the Linux kernel is programmed in C, but nowadays you can also write modules in Rust, which is maybe also quite interesting, but we will stick with C for this workshop. But you see, this doesn't look like a typical userspace C program. We don't have a main function here, because with a kernel module it's a little bit different. So in a kernel module we have a function which will be called when we are loading the module into the kernel, and we need a function which is called when we are unloading the module from the kernel. And with module init and module exit, we can set which functions will be called when the module is loaded into the kernel with init, and what function is called when we are unloading the module from the kernel with module exit. So my init needs to be a function with the return with an integer return value, 0 if everything worked fine, error code else, and no arguments. You can see this macro under init here. This is just for readability. So if you search for init or under init, you can also quickly find the function which is called when we're loading the module into the kernel. Okay, and what we are doing here is we're just calling printk. So we don't have printf available in the kernel because we don't have a standard output here. So we have to write it somewhere else. And where we will write it is the so-called Linux kernel's log. I will show you in just a second how you can check or see the Linux kernel log. And here we're writing hello kernel, the disaster takes its course. And here it's important always end your what you're writing to the Linux kernel's log with a newline character, otherwise it won't be displayed immediately. And then we're returning 0 to tell the kernel or to tell the user space the module was loaded successfully. So the exit function doesn't have a return value, and also doesn't need any arguments. And we have this under exit macro just to tell us, okay, this is a function which is called when we're unloading the module. And here we will also just write a line to the kernel's log. Here we are writing hello kernel, but the kernel got off lightly again, and new line. So for using printk and these macros and module init, module exit, we need to include two headers. So we need to include linux/module.h, and we have to include linux/init.h. These header files are shipped with our Linux header files. And then we have three more macros: module license, module author, module description. These are just metadata we can pass to our kernel. Author and description is optional, but you always have to specify a license. So here we are using the GPL license. And this is important because some Linux distribution only wants to load free and open source software. So if you would set the module license to proprietary, on some distributions you won't be able to load a kernel module because it's proprietary and the operating system only wants to load free and open source software. Yeah, so that's a first Hello World Linux kernel module. Now let's take a look how we can build it. So you have to know the whole kernel is built over a Makefile. And here you can see a simple Makefile to compile our kernel module. So first we are adding hello kernel.o to the variable object -m. So when you're compiling the Linux kernel and you're having a driver on hand, you can decide if you want to compile it directly into the Linux kernel. In this case, you would use object -y. And if you want to build it as a standalone Linux kernel module, you will add it to object -m. Or you can just not include it, then you don't have to add it to any variable. But we want to build it as a kernel module, so we have to add it to the object -m variable. And then we are defining two targets in our Makefile. We have an all target. The first target will be called when we are just running make, and we have a clean target for cleaning the build stuff. And what we will do here, we will run make again. With -c we can go into a different folder, and we will go in the folder /lib/module/shell uname -r. So let me show you this. Here I am connected to my Raspberry Pi, and if I run uname -r, you can see the kernel version which I'm currently running. And if I take a look at lib modules and then copying this kernel version in and go into build, you can see here are the Linux kernel headers installed. And here we also have a Makefile. So this Makefile will be used for building our Linux kernel module. But there's a problem. Our hello kernel.c file is not in this folder here. So we have to tell it, please look for kernel modules in a different folder. And the folder is pvd, so our current path we're in. And this m variable just is a variable to set where to look for kernel modules. And then we are calling the target modules from this Makefile, which will build us the kernel modules. So in theory, we could build multiple kernel modules at once if we would just add more names here to this object -m variable. Cleaning is quite similar. So we are also just calling a Makefile, the same Makefile again, the same path, but now the target is clean instead of modules, and that's basically it. Okay, so now let's say we have built our kernel module, and so at the end we will get a file called hello kernel.ko. KO stands for kernel object, and this is our loadable kernel module. So how can we insert it into the Linux kernel? Well, for inserting a module, we can use insmod, which stands for insert module, and then passing the module name which we want to load. If we want to remove our module again from the kernel, we can run remove module or rmmod. If we want to see which modules are currently loaded, we can use lsmod. And if we want to see the kernel's log, so we can see our two prints, we can run dm message. And another quite useful command is modprobe, because modprobe and the module name will load a module together with all its dependencies. But in order to be loaded by modprobe, the module has to be in this folder, unfortunately. So we will use insmod here in this tutorial or in this workshop. Okay, so now it's time you're doing your first exercise. Because this is a workshop, it should be interactive. Okay, here in my video, I will do it for you. So the exercise now is to implement a Hello World Linux kernel module on our Raspberry Pi, to compile the module with a Makefile, to load the module, to check the kernel's log and if the module is loaded, and then remove the module from the kernel. So we are using this Raspberry Pi, and you can see that I've plugged it with an Ethernet cable to my PC. So here on the Raspberry Pi, I'm running a DNS server, so my PC got an IP address, and then I could use SSH to connect to my Raspberry Pi. So yeah, let's create a first small Hello World Linux kernel module here. So I will name it hello, I will create a folder I will name hello, and in here I will add my Linux kernel module. So I will also name it hello.c. So I have Vim installed here. So let's include linux/init.h. And we will also need linux/module.h. Then let's add some description. So module license is GPL. The author is me. And the description is a Hello World Linux kernel module. Okay, then I will need an init function. And let's do it as a static, so it's only available within this module here. And let's use this init macro, and I will call it my init. And it doesn't need any arguments. And here I will use printk to print the line to my kernel's log, and I want to write hello kernel, and don't forget the new line. And then I will return 0 to indicate, hey, the module was loaded successfully. Oh, and I forgot to mention the type which is int here. Okay, then let's also implement the exit callback, which is called when we're unloading the module. I will call it my exit void function, and I will just print the line to the kernel's log, and I will print goodbye kernel, and that's it. And then with module init, I have to tell which function should be loaded when loading the module, and I also need to do the same for the exit function. Okay, so that should be it. Now let's create a Makefile. So first we have to add hello.o to our object-m variable. The substitution, so turning the hello.c file into a hello.o file, will be done automatically by the kernel's Makefile. Then I need an all target, and I will call the Makefile in lib modules. Then I will execute the shell uname-r command. So I will execute the command uname-r in my shell, and I need the build folder. So the path in which it should look for kernel modules is my current path, and I want to call the target modules. And for clean, it's about the same, but instead of modules, I will call the clean target. Okay, so now let me try to run this module. This will take a little while because the Raspberry Pi 1 isn't the fastest Raspberry Pi available, but we have time. Okay, now it's compiling. And soon it should start linking. Yes, done. And the output is this hello.ko file. Oh, I think I forgot to mention one useful command for here. So there is a modinfo command available, and if we're passing hello.ko, it will give us the metadata of this kernel object. So we can see our description, we can see our author, and we can see our license. We can also see against which kernel version this module was compiled. So with insmod, we can load our kernel module. And if we use lsmod and grep for hello, we can see this module is currently loaded. And if we take a look at the kernel's log, and I also want to see the tail of it, we can see here we have our hello kernel print. And if you're using our mmod to remove it again and take a look at the kernel's log again, you can see this exit function was called and the module is unloaded. Okay, so we have successfully fulfilled the first exercise. We have compiled a Hello World Linux kernel module, we have loaded it, and we saw that it was loaded and then we unloaded it. Cool. Okay, so now let's continue with some theory. Next thing we want to look at is how to control GPIOs. So to have a nice starting picture, I just printed the block diagram of a GPIO on a Raspberry Pi in here, but we're not in an electrotechnical lecture, so I won't go into details about this image. But basically here you can see with output functionality, with an input functionality, and we can add a pull up or a pull down. Okay, so now we want to control GPIOs. Therefore we have to following some steps. So first we have to request a GPIO, because in case it's already IO is already in use, we cannot request it. It's not available for our kernel module. So therefore we will use the GPIO request function, and here we have to pass in the GPIO number we're interested in, and we can also give it a label. This label will appear if you're running the GPIO info command, which is part of the GPIOD package. So if I run GPIO info, I can see all the various IO pins I have available. So on GPIO chip 0 I have 54 GPIOs available, and some already have names. For example, this pin here and this pin here is using for I2C, for example. But there are a lot of free IOs available, and here we can, so you can see which are unused, and we can give labels here. For example here, this should be the label. Okay, so in case the request worked, if it's not already in use, we will get a 0 back, otherwise an error code. In order to use the GPIO request function, we need the header linux/gpio.h. Okay, now we have requested the IO, so now we have to set its direction. So an GPIO pin can work as an input pin or an output pin. If we want to configure it as an input pin, we have to call the GPIO direction input function and pass in the GPIO number we want to use. In case this was successful, we will get 0 back as an error code. If we want to use a GPIO pin as an output, we will need the GPIO direction output function, which takes the GPIO number as the first argument and the initial value as a second argument. So if we want the IO to be 1 on startup, we will type a 1 in here. If we want to be, or if we want it to be 0 here, we will type a 0 in here. Okay, so now we have configured our IO pin. So how can we set the pin, or how can we read back its state? Therefore, we can use the GPIO set value command. Therefore, before we have to set the direction of this pin to output, and as arguments, this will take the GPIO number and the value. And you see it's a void function here, so you won't get an error code, for example, if you have configured this pin as an input previously. To read in the input value of a GPIO pin, you can use the GPIO get value function, and you only have to pass the GPIO number which you're interested in, and it will return 0 or 1 depending on the current state of the GPIO. Yes. And when we are done and we don't need the GPIO any longer, we have requested it, so we have to free it. And the freeing is done with the GPIO free function, and it just has to pass in the GPIO number which you want to free. Okay, this should be free and not enable. Okay. Good, so let's talk a little bit about this hardware here. So you can see here I have an IC available which will translate 4 I/O pins into the controlling signals of a 7-segment display. So we have a A pin, a B pin, a C pin, a D pin, and if I set all pins to 0, it will display a 0. If I only set D to 1, it will display a 1, and so on and so forth. So here we can see how to configure the pins and which numbers we will get. In case, for example, we're setting a 10 here, or any other combination higher than binary 9, the 7-segment display will be empty. Okay? And now I would say it's time for the second exercise. So the connections are: pin A is wired to IO11, pin B is wired to IO9, pin C is wired to IO25, and pin D is wired to IO8. And now you should write a kernel module which will initialize these 4 GPIO pins and the init function, which will set them to outputs, and then you should display a number between 0 and 9 on the 7-segment display, which number is of no concern. And the GPIOs, you have to release the GPIOs in the exit function again. Then you have to build and test the kernel module, and you have additional time. You can also initialize pin 24 as an input, because as you can see here, I have wired a button to it. So you can also read in the button state. So I would say, let's do this. So I'm back on my Raspberry Pi. Let me copy the hello kernel module, and I will create a new one, segment, I will call it. And let's jump into the segment folder. Okay. Yes, maybe I will run make clean first, so everything which was built is cleaned now. And then I will rename hello.c to segment.c, and I have to change this in a Makefile as well. Segment.c. Okay. So first let me change the description. Driver for a 7-segment display. Okay, and the first thing I have to do is I have to include linux/gpio.h. And let's change, so let's delete this here. Okay, and now let's define the IOs. IOA, so IOA is 11. Define IOB, this should be 9. Yeah. Define IOC, this is 25. And IOD should be 8, if I'm not wrong. No. And let's also define IO button. This was 24. Okay. So I will need a status variable here. And then let's start by requesting our IO pins. So I will use GPIO request for this. The first argument is the pin number, and the second one is the label. So in case status is not equal to 0, an error occurred, and I will print out requesting IOA, and I will return the error code here. And then I will just copy these 5 lines here and do the same thing for IOB. But here I already have requested IOA successfully, So here I should do a GPIO free of IOA. But then when I requested the next IO pin, I have to do a free of IOA and IOB. So the if statement here will get longer and longer and longer. And therefore, in Linux kernel modules, you will use something which is not so popular any longer for C programmers. So you will use go-to. So here, under return 0, under the good case, I will add a label called free_a, add free_a. I will free GPIOA, and I will return the status which contains the error code. And here I will just do go to free_a. Okay. Then again I will copy these 5 lines. And I will request IOC. And in case this fails, I will go to free_b. A little bit too much. I think I only need, I can delete these 10 lines here. And so now the cool thing is, in this case, free_b, I will first free IOB and then free IOA. And in doing it this way, I need much less IOs. Error requesting IOD, free or free_c, and here free_d. And this will be IO button. Okay, and I will go, So let me copy these 2 lines and copy them here. D, C, C, and I will also use a free button here, in which I will free the GPIO of my button. Okay. Okay, so now we have requested the IOs, so the next thing we have to do is we have to set the directions. And we can do this with GPIO direction output here. So let's set IOA, and the initial value is 1. And once again, if an error occurred, let me copy these 4 lines here. If an error occurred, I will go to free_d, error setting IOA to output, yes, and then I can copy these 5 lines for 3 times, and I do the same for IOB, IOC, and IOD. And the button I want to set to input, so I don't need any second argument here to input. Okay, and now last but not least, I have to display any value I want. So let's display 1, for example, with GPIO set value, IOA, and let's display 1 here. Okay, and in the remove function, what I have to do is I have to free all the IO pins. Okay, I forgot free_a. Okay, so this should be our Linux kernel module for setting up all the IO pins. Oh, I forgot to read the button state. So let's do a status is equal to GPIO get value, and I want to read an IO button, and then print k segment button, and let's print this out here. Okay, now I should have done everything. So let me close this and let me try to compile it, and let's see if I made any errors. Oh, free button defined but not used. Okay, so I made a mistake. I will, let me fix it. So here I always should go to free button and not to free B. So let's fix this error briefly. Here, and here, and here, and here. But I won't compile it again because normally I should not get into an error case anyhow. So now let me just load the module. Could not insert. Let's take a look at the kernel's log. Error requesting IOD. Okay, that's odd. Let's run GPIO info. We have pin 24, should be unused. Okay, let's check it. Error requesting IOD. Oh, yeah. Okay, this was the error. I tried to request IOB twice, but hey, now we have seen this error. So let's compile it once again. Now we shouldn't get any warning, and we should be able to load the kernel module this time. Yeah, Raspberry Pi 1s aren't really the fastest anymore. But I think we've compiled it successfully. Yeah, so let me load it once again. Segment KO. This time we could load it, and you can see now a 1 is displayed here. And if I remove it again, okay, the 1 stays here because I don't reset the value. But let's take a look at the button state. So here the button was 0, now I'm pressing the button and I'm loading the kernel module. And now if I take a look at the kernel's log, you can see now the button state is 1, so reading in the button also worked. Cool. Yeah, so we've successfully accomplished the second exercise. Okay, so now we can successfully initialize, set and unset GPIO pins. But there is one problem. We can only do this in the init and in the exit function. And we don't have any chance to manipulate the displayed number from userspace. So this is the next thing I want to add to my driver. And we will use device files, device numbers and character-oriented devices for doing so. But first let's talk about what are character-oriented devices and device numbers. Well, our interface should be a device file. We can see all the device files in the /dev folder of our Linux distribution. And you can see there are quite a lot of files. And the sense of all these files is to get an interface between a driver and your user space application. So let's take a closer look at some device files. The first one is our serial port AMA0. Then I want to take a closer look at GPIO chip 0, and I also want to take a closer look at the first partition of our SD card, which is MMC block 0 partition 1. So here you can see the output. At the left hand side we have our file name. Here we can see the owner and the group where this file is related to, and here we can see the file permissions. But what is this first character standing for? So we have a C and we have a B. Well, C stands for character-oriented device and B for block device. And this character-oriented or block device tells us a little bit about how to interface the device file. So here we have our serial port, and this is a character device. And this makes sense because on a serial port we're sending characters. So accessing it over a character device makes sense. And the SD card is a block device, which also makes sense because on a block device we are not transferring single bytes, so we are transferring blocks from the SD card into the SD card. And our GPIO chip is also a character-based device. And here you can see two numbers. The first one is the major and the second one is the minor device number, because the link between a driver and a device file is not made over a name, it's made about the device numbers. So for example, the GPIO chip is 254 minor 0, the SD card partition 1 is 179 minor 1, and the serial port is 204 minor 64. And if we want to see which device numbers are in use, we have to take a look at proc devices. And here we can see all the device numbers which are in use. For example, 254 is reserved for GPIO chip, 204 is for our serial port, and 179 is for our memory cards or other media cards. Okay, cool. And you can use such device files as any other file on your Linux machine. So I've written a small program I've named GPIO.c, and over this program we can manipulate an I/O pin. So basically what we're doing here, this program takes arguments. The first argument is the device file we want to use, and the second argument is optional, and this is the value we want to set to this I/O pin. Down here we are opening the device file, and then we are using I/O control to set the GPIO to output and to set the value. And that's basically it. And when I compile this, which will take some seconds, and if I run it, and let me switch on the camera for this, and using the GPIO chip 0 file and placing a 1 to it, you can see the display now has changed, and if I'm writing a 0 to it, we will unset this I/O pin. But I already said these device files are linked to a driver not by the file name, but over the major and minor device numbers. And we can create our own character device file with the makenode command. So let's do this. I will run sudo makenode. The first one is the name, and I will just name it test and put it in my home folder here. Then I have to say if I want a block or a character device, and I want to have a block device. And the major device number should be 254, the minor number should be 0. Okay, I've already created this file, so let's name it test1. And if I look here, we can see they have both the same major and minor device numbers. And now if I run my C program again, but now instead using test1 as the device file, and writing a 1 to it, you can also see that the LED value or the segment value has changed. So we could also successfully toggle the LED. So device files are not linked over the names, but over the major and minor device numbers. Okay. And the important thing is, in our init function of our driver, we have to register the device number and create a character device with it. And this we can do with the register character device function, which I will explain in more details just in a second. Okay, so what's the procedure if we want to use a device file within our driver? Well, basically we have to follow the following steps. First, we have to implement the system callback. So a file can have all the callback functions Linux is supporting, so read, write, open, release, I/O control, and so on and so forth. But we don't have to use or implement all the system callbacks, we just have to implement the ones we want to use. And then we have to bundle the callback functions in a struct, in a file operation struct. And you can see here, for example, this is how the struct looks like. We have a field module owner for the owner, and then we have the read, write, open, release, and all the other callback functions. Okay, so after setting up this struct, we have to create the character device, and we have to register a device number for it. This can be done with one function, but I will show you this just in a second. Okay, so let's take a look at the read and write functions callbacks, or the arguments which are needed. So first we have a pointer from the type struct file, which is a pointer to the currently open file. Then we have a string, or this under user macro just says this buffer comes from user space, and later we have to copy it to kernel space. So here we have the buffer in which we want to put in the read data. So this size t variable says how big the user buffer is, and then we have a offset, so a pointer to an offset, which is just the offset in our current file. We don't have to use this for our driver. And then we have the write callback. The arguments just look the same. The only difference is now our string buffer is a constant. So this just means on a write we don't want to manipulate the user buffer, and this is why it's a const char array. Okay, so let's take a look at how such a write callback could look like. So this is the implementation I will use in my driver. So the return value is size t, and this is just the numbers of bytes which were written successfully. And then we have the pointer to our file, we have the user space buffer, we have the amount of bytes to copy, and we have the offset in the file. Okay, so how can we create our character-oriented device and register a device number? Well, therefore we can use the register character device function. As the first argument is the major number it should use, it will automatically use the minor number 0. The second one is a string which will appear in proc devices. And the last argument is our file operation struct containing all the file operations we want to support with our character-oriented device. Okay, and the return value is an integer, so 0 on success, error code else. And of course, when we're registering something, we have to unregister it, and therefore we can use the unregister character device function. It takes the major device number as an argument and the label as an argument. And on success, it will return 0, otherwise an error code. Okay, in order to copy data, so we have the problem, this buffer here is a user space buffer. No, not this one here. And when we want to use this buffer, we have to copy this buffer into user space. Therefore, we can use the function copy from user to copy some bytes from the user space to the kernel space, and copy to user to copy bytes from the kernel space to the user space. So the first argument is always the destination. Then we have our source, copy from user. This is a user space buffer. Copy to user, the destination is a user space buffer, and we have the number of bytes we want to copy in this len argument here, and that's basically it. And this function returns the number of not copied bytes. So if it returns 0, all len bytes could be copied successfully, but if it would return 4, for example, then 4 bytes could not be copied successfully. Okay, so how can we interface our device files from the bash shell? Well, I also already showed you the make-not command. So the make-not command will create a device file with the name we can put as first argument. Then we have to put a C here to tell it it's a character device. We will use major number 64, minor number 0 here, and this will create us the device file /dev/sec. In order to write to the file from the bash, we can use echo and just pipe this into our device file. And this will write the string 7, new line, and a 0 to the device file dev/sec. But it's important, depending on the access permissions to this file, maybe we have to run this command as root. And to read from a file, we can use cat, but this cat has a downside. Cat will only terminate or stop reading from the file if read returns a 0. And to have this, we would have to use the offset in the file. And depending on the file permissions, you may have to run this command as root. And if you just want to read out a line until the next new line character, you can use head -n1, so reading out one line from the file dev/sec. And also depending on the permissions, you have to run this as root. Okay, so now let's come to the next exercise. So your task is, you have to assign the major device number 64 in your init function and create a character-oriented device for it and release it again in the exit function. Then you have to implement the write callback so we can display the number from 1 to 9 on our 7-segment display. Then of course you have to test the driver, and the additional task here is we also have a button available here. So you can also implement a recallback which will return the current status of the button, and that's basically the task for now. Okay, so now that we have the theory on hand, let's implement a character device file or a character device compatible driver for our 7-segment display. And sorry for not turning off the camera. I hope it was not too distracting, the last part. Maybe I will record it a second time. Let's see how much time I have after this workshop. So I will navigate into my segments folder and I will open up the segment.c file. Okay, and first I have to include I have to add a new include. So I will include linux/fs.h, and I will add a new define, which I will call my major. So this will be the major device number, and this should be 64. Okay, so down here, after all this initialization stuff, let's delete these 4 lines, we don't need them. Let's I have to take a look how the function is called. I think it's register character device. So the first argument is my major. The second one is a label, so let's use segment here. And the last one is the file operations. So I haven't implemented them yet, but I will do this just in a second. And in case the status is not equal to 0, an error occurred. Error registering my major or creating character device, and I will go to free button to free all the IOs, and here in the exit function I have to unregister the character device, and here I don't need to pass in the file operations. Okay, so now I can implement the callback functions. So I will start with the read function because this is the mandatory one. The first argument is a pointer to the currently open file. The second one is the data, which comes from the user and which should be written to our device. Then we have the number of bytes. This buffer is big. And last but not least, we have this offset, but I think I won't use it for this driver. Okay. And I'm a little bit lazy, so I will do it a little bit simpler than in the example. I mean, you can take a look at the example too. So all I will do is I will check if the count is bigger than 0. And if so, or U8, and if so, I will set the value to buff 0 equal to 1, or no, minus 0. So I mean we're just passing this buffer. Normally will be, for example, the number and a new line. So I'm just picking the first character here and that will be it. And then I will display this. And at the end I will return the count. Okay, and now I have to set up the display. So I will use GPIO set value. So I want to set IOA, and this is val and 1. So, and I need the same for B, C, and D. And this is well and 2. Greater than 0. This is 4 greater than 0. And 8 greater than 0. Okay, and this is how I will set the variable. So this is not the best way. I don't do an error detection or something like that, but it's convenient for me now, so I will go with it. And now let's implement the read function. I will call it my read. So the first argument again is a pointer to our currently open file. Or now this is now not a const char, only a char pointer. And here I need a value 2. So first let's read out the button, and I can do this with val is equal to GPIO get value. I want to read IO button. Yeah, maybe let's use a string here, or yeah, char buffer. Yeah, 8 chars are enough here. So int to copy is equal to so if count is bigger than 8, yeah, this will be count, or this will be 8, else it will be count. Okay. And then let's do an sprintf, or maybe an sn printf. So the first one is our buffer. The second one is this string here, and then the argument, which is value. And the last one, let me look it up. I hope I have man installed here. Printf. Yeah, I do. So sn printf. Okay, the size goes before the format. Okay. So here I have to copy. Here I have to add 2 copy. Or maybe let's use an 8 here. Okay, and now let's copy to user space. And copy to user. So let me check the arguments one again. So first is the destination, then the source, and the length. So the destination is buff, the source is buffer, and to copy is the length. So this will return the number of bytes which haven't been copied. So in a good case it will be 0, and here I'm returning the red bytes. Okay, then I can implement my file operation struct. File operation or file operations. Let me check. File operations. And I will call them fops. And I will just assign the read callback and the write callback. Okay, so that should be it. Let me try to compile it. Let's see how much mistakes I made. Okay. Static struct file operations. Okay. Ah yeah, I forgot an equal sign here. Register. Oh, and this should be unregister. Yeah, so let's fix this. So here I need an equal sign. And down here I will need an unregister. Let's build it again. At least these two errors should be resolved here. And this one as well. Okay, now it's looking good. So, yeah. So let me load my module. It was loaded successfully. Then let's grep proc devices for segment. So here we see segment has now allocated major device number 64. With makenode we can create a device file. I will call it segment 0. It should be a character device, my major 64 minus 0. And now I will change to root user. And I will echo a 2 to dev segment. So let me turn on the camera again and let's see if this works. Hey, we have a 2 here. So for I in sequence 209 do echo I sleep half a second, done. And now it should be count up from okay. Yes, I think I have an error here somewhere. So yes, I have mentioned D twice, so this is the error here, but never mind. And now let's try to read in the state of the button. So it's 0, now I press the button, now it's 1. Hey, cool, so we have successfully created a character device over which we can communicate between the driver and the user space, and now we can control our segment display, and we can also read in the state of this button here. Yeah, cool. So that's basically it. So let me check if I forgot something here in my slides, but I don't think so. No. So the rest of the topics is additional. If you're interested in these topics, I've already made videos on my channel here, but if you want me to go through this slide deck on another location or occasion, please let me know, then I will do a video about it. So I guess this was my Linux driver workshop for 2024. I hope you've enjoyed it and learned something. In case you want to support my work, you can buy my coffee on buymeacoffee.com/Linux. So that's it for today. Thanks for watching and goodbye.